The recording is not starting. No?
It started. I mean.
It started. Okay.
I see that the red.
Okay, now it is. Okay, now I see. Okay, thanks. Okay, good afternoon, everybody. Today we have the 7th, I guess, remote talk in the astrophysical seminar in the Bologna campus. And today's guest is Eline Maaike De Weerd from the University of London, Queen Mary University of London. And she's speaking from London, of course. Just a short introduction, she graduated from the University of Edinburgh with a degree in mathematical physics in 2017, and then started her PhD at the astronomy unit at Queen Mary, and she's supervised by Clarkson and Purzido. And now she's in the course of her final year. And she will tell us today about the use of galaxies for cosmology, and in particular, she will speak of the relativistic galaxy bispectrum. So please, the stage is yours.
Okay, well, thank you very much for introducing me, and thank you for giving me the opportunity to speak in these weird times. So I'm going to talk about the relativistic galaxy bispectrum, and I realize not so many people in this group might be familiar with the bispectrum or cosmology. So I'll try and really explain what I'm doing. There will be some equations as a word of warning, but I will try and explain sort of the important bits. I don't think you can see my mouse, but I will try and kind of explain the bits of the slides that I'm talking about. So this is based on 3 papers. Have all been accepted for publication, so more details will be in that. And it's based on work I've been doing with my supervisor, Chris Clarkson, Stefano Camera, who's in Torino, and then some collaborators, Xian, Roy in South Africa, Obina in Portsmouth. So first, let me try and motivate this. So what am I working on? Well, I'm working cosmology, and we're entering what's now called the era of precision cosmology. So that's buzzwords. What this means is that there will be future surveys, such as the SKA, Euclid, other surveys like that, and they will be like observing the universe, observing galaxies at higher precision, higher redshift, higher, like more new information will be available. And to be able to use this information as best as we can, we need to improve our theoretical modeling. And that means that the bispectrum, as we call it, will be increasingly important for improving these cosmological constraints. And then let me try and explain what this bispectrum is. So let's first take a step back. How do we study the universe? Well, we study fields in the universe and statistics of this. And if you have a purely Gaussian and statistically homogeneous and isotropic field, it's fully described by what we call the power spectrum, which is the Fourier-space equivalent of a 2-point correlation function. So the first equation there is the definition of the power spectrum. So you have a correlation between these 2 deltas, and these are overdensities at different k vectors, different wave vectors. On the right-hand side, there's this delta function, k plus k prime, so that basically means that you're correlating 2 of the same scales, and this p of k, which is what we call the power spectrum. And the power spectrum is what has been used so far primarily to constrain cosmology, constrain cosmological parameters, etc. But a property of Gaussian fields, for example, is that they have vanishing odd correlations, and you can only do so much with them. And if you want to look at more interesting fields with non-Gaussian statistics, you need to look at higher order correlators. And the first of these is what we call the bispectrum, so that's the thing I'm studying. And that's the second equation on this slide. So you have now a correlation between 3 deltas at 3 different wave vectors. And this is like the Fourier-space equivalent of a 3-point correlation function. So we've gone up from 2 points, which is the power spectrum, to 3 points, which is the bispectrum. On the right-hand side of this equation, there's a delta k1 plus k2 plus k3. So what this means is that you have essentially a triangle formed by these 3 wave vectors you're interested in, forms a closed triangle, and this b, k1, k2, k3, and that's what we call the bispectrum. So it's really just one step up from the power spectrum, and it will contain information that's complementary to the power spectrum and some extra information as well. So move on. Why are we interested in this? It's because we're trying to understand and study the universe. And the universe is not Gaussian, as many of you might know. There's, for example, primordial non-Gaussianity, which is usually characterized by this FNL, this non-linearity parameter. And this is something that's predicted by, for example, various theories of inflation, other theories of the early universe. So this is something you would be interested in trying to measure and constrain if you want to study how like the early universe evolved. And then also as the universe evolves through time, there will be structure formation under gravity, so nonlinear evolution of structures of matter, etc. And this introduces some non-Gaussianity in the universe. And also because when we observe galaxies in the sky, for example, we're observing light coming from these galaxies. So you're essentially observing on your past light cone. And that means that this light is subject to relativistic effects, and these relativistic corrections, they can actually mimic this primordial non-Gaussianity on large scales. If we're looking at these large scales, which new surveys will do, we want to study non-Gaussianities in the universe to really distinguish this signal from these relativistic corrections from, for example, primordial non-Gaussianity. So that's some motivations why we're interested in something like the bispectrum. Now, to make this a bit more tangible, like what does the bispectrum look like? I have this slide, which is from a paper I really like by Anthony Lewis. And let me try and explain this, which is a little bit difficult without a mouse and doing it remotely. But on the left-hand side, there's a plot of, in this case, an equilateral bispectrum, which is just an equilateral triangle. And how you can kind of envision this is as being sort of plane waves. In this case, it's T, K1, K2, K3, which is in this case temperature waves, but it would be similar for example, density fluctuations versus temperature, etc. It all works the same. So what these are, this is three-dimensional, and it's just a slice through of like three-dimensional plane waves of overdensity, underdensity, which is denoted by the colors here. And then on the right-hand side of the figure of the left, there's these B's and these like interesting weird structures, yeah? So if you have a positive bispectrum, so B larger than 0, you have very bright dots surrounded by like the blue purplish. And this means that you have concentrated overdensity surrounded by a sort of net of underdensity, and vice versa for a negative bispectrum. So if you then look at the figure on the right, which is just a screenshot of the Millennium simulations, you see here that you have a sort of network of kind of bright, of overdensity, what we call like bright galaxies form a sort of net-like structure surrounded by voids. Now, this is like a three-dimensional projection, but if you would do a slice through of this, what you get is you get concentrated networks, like filaments of overdensity surrounded by underdensity, and that then corresponds to a largely positive equilateral bispectrum. So that's sort of how you connect the bispectrum, which is this abstract Fourier-space thing, to whatever you would see in real space. The other thing to keep in mind is that this would be something that is on average, so it's not really that space everywhere would have to look like this. So like on the Millennium simulation, you also see that there are some bits that have like more brightness, more galaxies, more overdensity, but on average it would be largely positive equilateral bispectrum. So I hope that's kind of clear. Then the last thing I want to touch on in the motivation is this primordial non-Gaussianity I was talking about. So on the left-hand side here is a plot of an earlier paper that my supervisor did with collaborators. And what this is the bispectrum for two different triangle configurations, because we're dealing with these three wave vectors. You can have equilateral, which in this case is the red lines, versus like squeezed, when one of the sides of the triangles would get very, very small and you're looking at very large real space modes, and that's the blue lines in this. What else is there? There's the dashed lines, and this is just Newtonian, so without any relativistic effects that come in on a past light cone. The solid lines are including these relativistic effects, and you can see as you go to the larger scales, so larger scales correspond to small k. So on the left-hand side of the plot, you get this divergence of like these GR effects, these relativistic effects from the Newtonian prediction. So on these larger scales, these relativistic effects will have a larger signature. So it's important if you look at these scales to include these. On the right-hand side is that the primordial non-Gaussianity would wrongly assume if you neglect these relativistic effects. So if you compare only your primordial non-Gaussianity with a Newtonian bispectrum, you would very much overestimate the amount of primordial non-Gaussianity you have in the universe. So if you would properly include this, you can actually, like, hopefully distinguish these signals. Is that clear so far? Okay.
Yes,
I assume
I cannot speak for the others, but we can
Excellent.
hear everything well.
Okay, so then let me move on to these relativistic corrections. So like I said, we observe on the past light cone. And if you do this, you project this galaxy number count fluctuation. So that's kind of the difference in these galaxy number counts you do. When you observe, you can divide like in bits of solid angle, redshift bin. And you do galaxy counts in those like little blobs you have then. And there's some fluctuation that's what we're interested in. When you project this in the past light cone, you have different effects that come in. For example, the Kaiser redshift space distortion, which is quite well known and studied, Doppler effect, Sachs-Wolfs, etc., etc. And if you go to nonlinear order, there's also couplings between these effects. So this really gets quite theoretical and quite complicated quite quickly. So let me now show some equations. So don't get too stressed. I will try and explain like what's going on here. So if you look at first order in perturbation theory at the galaxy number, galaxy density contrast, so that's this delta 1 that I've put there. You see that you have some Newtonian bit, and Newtonian here is anything that doesn't have this h over k in there. So just these first two terms, b1, f, that's just some growth, some clustering, that's the Newtonian bit in this. And then you get some relativistic effects coming in at h over k. At second order, you get a leading correction, so that's this delta 2g. The galaxy density contrast at second order gets a leading order correction as h over k, but this is imaginary. It has an imaginary I in front of it. But now, if you consider the power spectrum, this 2-point correlation function, or the Fourier-space equivalent to that, which I mentioned before, for just a single tracer, you get these relativistic effects coming in as h over k squared. So that means that it's suppressed when k is larger, yeah? That's because you get delta g times delta g star, and like the average of that, ensemble average of that. So that's how it works in the power spectrum. But now if we turn to the bispectrum, the leading order corrections, the relativistic corrections come in as h over k actually. Because the bispectrum you would have delta g, and the second order delta g. So if we go back to the previous page, it means you have this leading order delta 2g, which has this imaginary bit, and just h over k in there. So what does this mean? Like, this is a lot of like h over k factors floating around in this. What it's really just saying is that in the power spectrum you get h over k squared. Bispectrum you have these relativistic bits coming in as h over k. So that means that they're less suppressed in the bispectrum for a single tracer, and probably more accessible if you're interested in measuring these relativistic effects, which is what we want to do. So far that's another reason why the bispectrum would be interesting. So more equations, so don't freak out. The bispectrum is just this correlation between these galaxy number counts, yeah? Which is the first equation on the left-hand side, these big deltas, the galaxy number count fluctuation, and again this bispectrum Bg and this delta. And then I've put in like a little drawing of a triangle formed by these three wave vectors, and n here is the direction of line of sight, so just an observer looking at some triangle. And the bispectrum itself, this B of G, is a product of Fourier-space kernels. So those are these weird curly Ks, and then it goes as power spectrum squared plus cyclic permutations. Don't worry too much about it. The only thing I want you to keep in mind from this is that these curly Ks, these Fourier-space kernels, can be split into a Newtonian and a relativistic part. The Newtonian part is generally well studied, and it looks like this. So you have at first order some Newtonian bit, second order some Newtonian bit, and the only thing you really have to memorize from this is that none of this goes as h over k. This is all k to the 0, yeah? And this incorporates various Newtonian effects, just which are well studied, like second order density, second order velocity, these clustering biases, which is B1 and B2. And then second order redshift space distortions, which, for example, in Z2, S2 is tidal bias. This is just what you get from perturbation theory. It's really quite complicated to calculate, but this is just Newtonian. Then if we look at the relativistic bispectrum, which is the thing I study, at just the leading order, so most of what I'm going to say is about just this leading order, just anything that goes as h over k, you get this mixing of at first order relativistic and second order Newtonian, or just first order Newtonian, second order relativistic. That's all that this is saying. So you have a Newtonian part of the bispectrum plus some relativistic part of the bispectrum, and this is just this leading order, yeah? So you get first order relativistic effects, second order relativistic effects in this. And why are these interesting? Well, these leading relativistic corrections to the bispectrum, and don't worry too much about this whole massive equation. The only thing you really need to know is that there are imaginary i's in this. This is a purely imaginary addition to the Newtonian approximation. So the Newtonian bit of the bispectrum at leading order is just real. This is purely imaginary. Now, one thing you could do is you could expand the bispectrum in invariant multiples about the observer's line of sight. So what you get out of this is these BLMs. Those are the invariant multiples, and that's interesting because these are invariant. You could maybe construct estimators for that, etc., etc. And at leading order, the monopole of the bispectrum is only the Newtonian part, and the dipole is only from the relativistic correction. So that means if you can measure dipole, this is a smoking gun signal for the leading relativistic corrections. So we've made some plots of these. On the left-hand side is for a galaxy survey like Euclid. Right-hand side is for intensity mapping, so something like the SKA. And what you can see here is the black line is the monopole, so this is purely Newtonian. And the red and blue lines is the dipole, so this is purely relativistic. And what this is a function of triangles, function of triangle shape. So either the angle theta between K1 and K2 is changing, or K3 is changing, and plotted on the right-hand side. And on the top, you see these little triangles, so they show you what sort of triangle shape you have. And you can see that the dipole, so this thing that's purely relativistic, is really quite large compared to the monopole. This is kind of the same plot, except that now we've picked out two triangle shapes, the flattened one and the squeezed one. And again, you can see that the dipole, so the red lines and the blue lines, they're quite large, like about 10% on the equality scales of the monopole amplitude. The other thing in this you might notice that there's like for the blue and the red lines, there's this discrepancy between a dashed blue or red line and the solid one. Well, in this case, the dashed one, this is including some Newtonian corrections where the solid line is relativistic, so you get this divergence at the larger scales. So what we've seen is that the leading relativistic correction to the bispectrum is a dipole with respect to the observer's line of sight. And in contrast to the power spectrum, this dipole exists even for a single tracer. It vanishes identically for the equilateral configuration. I haven't really shown that explicitly, but you can do this analytically as well. Full details are in this paper. And even on equality scales, amplitude is about 10% of the monopole. So that's interesting because that means maybe we can detect it. So let's look into that a little bit more. Because, yeah, can future surveys detect these relativistic contributions? So we've done this for a Euclid-like galaxy survey. Just considering the signal-to-noise ratio. So I've written the equation there, don't worry too much about it. We've just worked out the signal-to-noise for this. What does this look like? Well, it looks like this. So on the left-hand side, we have the signal-to-noise per redshift bin for something like Euclid. Peaks at around 6, 7. On the right-hand side, we have the cumulative signal-to-noise. This is adding up for each redshift bin. And it goes up to 18. Now, if you remember, we had this splitting of like first order relativistic effects and second order Newtonian. And first order Newtonian, second order relativistic. What if we leave out these second order relativistic corrections? Like, do they really matter because they're quite complicated? Turns out they actually do matter. Here, the dashed dotted lines is omitting these second order relativistic corrections. And you see that the signal to noise you get really drops quite significantly. So that does show that you do need to include these second order relativistic corrections. They are an important part of your bispectrum.
5 minutes.
Okay, thanks. So we've looked at the cumulative signal to noise for a stage 4 spectroscopic survey similar to Euclid, and we've seen that this is of the order 10 for just the leading order relativistic corrections. What is this sensitive to? It's sensitive to change in the non-perturbative scale K max. That's where perturbation theory is starting to break down. And we've used a conservative redshift-dependent K-max. And it's also sensitive to change in B, E, and Q. So these are the evolution and magnification bias. And it's important to model these self-consistently from the same luminosity function produced in number densities. Full details are again in that paper. And then the last thing I want to have a brief look at is higher order multipoles. Because so far I've really looked at the monopole, which is only the Newtonian bit, remember, from the earlier plots, and the dipole, or the leading order relativistic corrections, which is what we looked at with the signal to noise. But there are higher multipoles in the bispectrum as well, if you do this decomposition, and you can do this decomposition fully analytically. It's quite a long and complicated calculation. Full details are again in that paper. If you're really interested, have a look at that. And the main takeaway from this is the Newtonian part has only even multipoles, up to and including L equals 8. If you include relativistic corrections, you get even and odd multipoles, up to including L equals 7. And I've illustrated that in the plot on the right. I know this is a lot of like weird, scary lines, so let me take a moment to try and explain what's going on here. So this is the normalized power that's contained in the bispectrum. So it's basically all orientations, so all values of m of the multiple expansion of the bispectrum divided by the Newtonian monopole. So Newtonian L equals 0. So the dotted lines are just the Newtonian. Solid lines are Newtonian plus relativistic corrections. So what you see is that, for example, L equals 0, L equals 2, L equals 4, that's all purely Newtonian or Newtonian plus relativistic, and you get this divergence at the larger scales when the solid lines start to diverge from the purely Newtonian dotted lines. But the main takeaway is that this dipole I mentioned, which is L equals 1, but also the octupole, for example, which is L equals 3, get large on larger scales around equality scale. So that means that if you want to study and measure the bispectrum, you want to look at these higher multipoles as well. And it is important to include these relativistic corrections. Otherwise, don't worry too much about that figure. So then let me have a brief outlook. So we looked at signal to noise only for Euclid. We want to do something similar for the SKA, where of course you have like beam effects, etc. We want to do some Fisher forecasting, Fisher matrix analysis for relativistic bits of the bispectrum. And we want to include primordial non-Gaussianity because all of the calculations we've done so far are assuming Gaussian initial conditions. So then I will end on my summary. I've hopefully shown you that the bispectrum is important for future surveys, for improving constraints, discriminating between theories of the early universe, etc. There's these leading relativistic corrections to the bispectrum, which is a purely imaginary Doppler-type correction. And if you can measure this, it's a smoking gun signature of relativistic corrections. This has an amplitude of about 10% of the monopole and equality scales. And for a stage 4 spectroscopic survey similar to Euclid, it has a signal-to-noise ratio of order 10, which means it's potentially measurable. And then there's this last bit about decomposition of the bispectrum in invariant multipoles, which can be done analytically, and you can show that it's important to include these relativistic corrections, especially when you look at larger scales. So yeah, thank you, and I'm happy to answer questions.
Okay. Thanks. So here we are. So while maybe cosmologists think about questions, I would ask some simple one from on my side. I'm not a cosmologist myself. When you speak of future survey, does this imply all these forecasts are done assuming a full sky coverage? I mean, how critical is to define the area of the survey? Or
Well, the area comes in, of course, in for example, when we calculate the signal to noise. But if you look at, for example, this plot I showed of Euclid, you can see per sort of redshift bin the signal to noise in that. So from this you could deduce or just very easily like cut off bits of your redshift coverage.
Okay. Now we have a cosmologist for a question. Laura, please.
Okay, thanks for the presentation. So I have just a curiosity. What is, in your opinion, the advantage of using the bispectrum in spite of the 3-point correlation function? So why is better to use the key space in spite of the real space?
There isn't really an advantage. Some calculations to include all these effects are easier done in Fourier-space, which is why you prefer to work in Fourier-space. But for example, if you want to include, say, wide-angle correlations, that's something that's very difficult to do in Fourier-space. So for those things, it would be better, I think, to move to real space. It just depends, like, what you're trying to calculate, what you're interested in, I think.
Okay, thanks.
Then we have Carlo Giocoli, please.
Very nice talk. Hi. So I wanted to ask you something. So suppose that I want to construct a light cone from a numerical simulation. How can I design my experiment, constructing the light cone from numerical simulation, to be able to have something measurable of those relativistic effects?
How do you construct your experiment? I don't really know too much about that, to be honest. How do you, sorry.
So I have to construct a particular numerical simulation which has this signature. And so going back to the question that Franco asked, so how wide should be the light cone that I construct in this case? And does this signal also depend on the extension in redshift of your light cone?
So extension redshift, so like you see in these plots I have up at the moment, and most of the other plots I've shown, they're actually all at redshift 1. One of the issues with the analysis I've done, and something that we're looking to include as well in future work, is that it excludes wide angle correlations and assumes like plane parallel. So to properly do this sort of light cone analysis, you would have to include these wide angle effects as well and integrated effects. How you construct a light cone is not something I know a lot about. Some of my collaborators, like Julian Adamek, who wrote G-Evolution, which is this light ray tracing code, might know a bit more about that.
Okay.
I'm not sure I can answer your question satisfactorily.
Okay, thank you.
Sorry.
Thank you.
Okay, now Moscardini have a second question, please.
Okay, thanks. So I have a curiosity. So is it simple to do the same computation for weak lensing observables? So in principle, because when you mention Euclid, I assume that you are mentioning only the clustering part of Euclid, but Euclid will also have the weak lensing part. So in principle, it's not so difficult to extend your computation for weak lensing, I assume, or not?
Maybe. So my computation, like, it looks quite simple, but really to calculate this is very complicated. There are very, very many terms that come into play in here. So I think while you might be able to extend it, it would be very difficult. There are some effects that we do include in this already, but we focus mostly on galaxy clustering, galaxy counts. Okay, thanks.
So going back to the question of Lauro. So the thing is that when you do lensing, it should be a little bit straightforward to do this integral along the line of sight, right? Because in this case, when you do the clustering, you need to assume a bias parameter to trace the galaxy tracing the dark matter density distribution, while when you do lensing, I think you need to do only an integral of the, let's say, matter density perturbation up to the second order or third order along the line of sight. Okay, you know someone that has done something like this, for example? Are you aware?
I don't know.
Okay.
Okay, thanks. Any more questions from the audience? I don't see anything else. Okay, so I think that finishes our talk. Thanks a lot for being our guest today.
Yeah, thank you.
It was a nice talk, and all the best for the last year of PhD, wrapping up the thesis and everything else.
Many thanks.
Okay.
Yeah, stay safe, everyone. I will try and stop sharing this.
Well, now I'm stopping the recording.
Okay.